compound interest is similar to simple interest, except for one huge caveat. The interest is calculated periodically, maybe twice a year, maybe every month, maybe every day. It's calculated periodically, and then it's added on to the principal, so that the next time you calculate interest, the last interest is considered part of your principal. So as the loan or the savings grows, the interest is being calculated on that growing principal balance. Let me show you what I mean. If we invest $100 at 8% annual interest, now that's unreasonable. Nobody's going to give you 8% annual interest for that small of an investment. But just for the sake of illustration, let's assume you put $100 into the bank, you get 8% annual interest, and it's compounded quarterly. There's a few things here that are jumping out at us I want to highlight. Our initial deposit is $100. 8% annual interest, that's like our interest rate, but it's compounded quarterly. Quarterly means 4 times a year. Can't read year there. Let me fix that. We want to know how much the account will have after 1 year of this compound interest being calculated. Which basically means we're going to calculate interest 4 separate times. Each time we calculate it, we're going to add that interest we calculate to the principal so that the next interest calculation includes the last interest. So for the very first case, there has never been any interest calculated. So that first quarter, the initial amount is the $100. The final amount is going to be the 100 times our interest. So each quarter, the interest is going to be the annual interest, which was the 8%, divided by the number of times that we are calculating interest each year. So if we look at 8% and we say quarterly, we're compounding it 4 times a year. So that's like 8% divided by 4. In other words, that is 2%. So if we're looking at the final amount, remember this is just like simple interest, but we're repeating the process multiple times a year. So our simple interest, the final amount was the principal plus the interest, which we said shortcut calculation for that was principal times 1 plus our interest rate times time. Our time is going to be 1 period, so it's going to be times 1. In other words, this is going to be our interest rate plus 1. So if our interest rate is 2% and we add 1 to that, that would be like 0.02 plus 1 or 1.02. So this is what we will multiply to our principal every time we're calculating the interest each quarter. Again, how did we find that? We said 8% annual interest compounded 4 times a year. So annual interest divided by the number of compounds each year gave us 2%. Specifically, to find the final amount, we know we need to add the principal plus the interest. In this case, that turned out to be principal times 1.02. That's the 1 plus the interest rate. So our final amount would be 100 times 1.02. And then that amount, that final amount, now becomes the initial amount for the next compounded interest period. Parentheses so we don't get confused between our decimals. Now the next compound, the second period, we're going to multiply again by 1.02. So we'll have 100 times 1.02 times another 1.02, which I could write like this, or I could say 1.02 squared, which I like that better. That final amount becomes the next initial amount. When we compound the interest after the third period, we multiply by one other factor of 1.02. So instead of 1.02 squared, That's going to become a third factor, 1.02 cubed. That final amount will become the next initial amount. And then on the fourth quarter, we compound one more time. So our final amount looks like 100 times 1.02 to the fourth power. Hopefully, we see a pattern here. Our final amount is equal to our principal times 1 plus the interest rate. Remember, our principal was $100. 1 plus our interest rate. And then the exponent here is rate times time. And actually, let's copy the format of the book, and instead of call that rate times time, we're going to call it N, where N represents the total number of interest calculations. In this example, we calculated the interest 4 times. That's because we compounded quarterly for a total of 1 year. So technically, it would be like 4 interest calculations per year for a total of 1 year, like 4 times 1. In other cases, you have to calculate this a little bit differently. So we'll talk about that in another example. But notice that the pattern is following this principal, parentheses 1 plus the annual interest rate, sorry, not the annual, the quarterly in this case, or the periodic interest rate, and then that's raised to the total number of interest calculations. So in this case, when we invested $100 at 8% annual interest compounded quarterly, the final amount after 1 year of this type of investment would look like 100 times 1.02 raised to the fourth power. The final amount is $108.24 rounded to the nearest cent. If we had let this go on, maybe instead of calculating it for just 1 year, maybe we had said, let's do 3 years. A lot of this would stay the same, except for this table would need to extend for another 2 years. Right now, we made a table for 1 year. We'd have to continue it for another 2 years. We don't have to make that table, though, because we found a pattern. We found that the final amount is going to be principal times 1 plus the periodic interest rate raised to the total number of interest calculations. Our principal is $100. We know that when we compound quarterly at an annual 8%, that rate was 0.02. Now this is where I'm talking about the exponent is different because we're compounding quarterly over the length of 3 years. So that's compounding 4 times a year for a total of 3 years. So if we had let our investment sit that long, instead of having only $108, we would have $126.82, rounded to the nearest cent. So with compounding interest, we need to know more than what we needed in the simple interest situation. And that's because we need to know how many times are we compounding each year. Once we know that, we can find the periodic interest. In this case, it was the interest for each quarter. And then we can plug that into our formula and calculate. Let's try another example. Suppose you deposit $1,000 into a savings account that pays 6% annual interest, but it's compounded quarterly. We want to know what's the balance after 1 year. To find that balance, we're going to calculate the final amount, which is our principal, times 1 plus the periodic interest rate raised to the nth power. So our principal is 1,000. Multiply that 1 plus our interest rate, which we need to calculate. If we have 6% annually, but we compound it 4 times a year, that's going to look like 2/3% every quarter. Maybe we remember 2/3 is 0.6 repeating. So if we turn that into a percent, 0.6 repeating, that's going to look like 0.006 repeating for the decimal version of that percent. Now, if we tried to plug in 0.006 repeating into our calculator, it might spaz out on us. So although those things are equal, maybe using the decimal version in this case is not ideal. This is where fractions might be our friends. If we look at 2/3%, that's the same thing as 2/3 over 100. That's the same thing as 2/3 divided by 100, which is the same thing as 2/3 times 1 over 100, which is the same thing as 2 over 300. Now, if you had typed 2 over 300 into your calculator, you'll get that value, 0.006 repeating, but this is the exact value. And our calculators can handle that. They can't handle this repeating notation. We don't have a button for that, or at least my calculator doesn't. So my interest rate for each quarter is going to look like 2 over 300 instead of using that 6 repeating notation. Then we need to calculate N, the number of times that we are calculating interest on this investment. For 1 year, compounded quarterly, that's going to look like 4 times a year for 1 year, 4 times 1. Not 4.1, but 4 times 1. So that would look like 1,000 times 302 over 300. And that fraction is raised to the 4th power. We can type this into our calculators. And I get a final amount that looks like, oops, I missed a 0. I've got to retype that in. Always double check your calculator work. It's easy to have a finger slip. So my final amount is $1,026.93 rounded to the nearest cent. If we wanted to know what the effective annual yield is, that's basically saying how much did your money grow? And we can quickly calculate that in this instance because the numbers are pretty simple. We had an initial deposit of $1,000. We have a final deposit of $1,026. So that effective annual yield, I'm going to appropriate that. Oh gosh, I'm at a loss for words here. I can't remember what it's called when you abbreviate. There we go. I'm going to abbreviate effective annual yield as EAY. And that would be the initial deposit, $1,000. Sorry, I'm subtracting that backwards. It would be the final amount, $1,026.93, minus that initial deposit. That gives us $26.93. So that effective annual yield, that's the amount that the money grew because of this interest that we're calculating. Compounded interest has a few very common phrases that I want to make you aware of. One is compounding quarterly, that's 4 times a year. There's also a semi-annual compound, that's twice a year. If you come across a wording of a problem that's asking you for compound interest, make sure that you read carefully and look for any clues that tell you how often it's compounded. And of course, if you don't recognize the word, do a quick internet search, see if you can figure out how many times each year they are compounding the interest. Now, if we were to compound interest once for the entire year, that's exactly the same thing as saying simple interest. But every time we increase the number of compounds in a year, that's where it's going to change between simple and compounded interest. And maybe you recognize that this is actually a geometric pattern because we're multiplying each year by the interest rate. So the last term multiplied by this common ratio, just like the geometric sequences that we saw in the beginning of the semester.